Vergari. Ah, Vergari, okay, Vergari. So just connect it. Yeah, connect the old.
You fly out tomorrow early.
Yeah. 7 a.m. 6:58 a.m. That's okay. There should be no issues with flying.
Yeah, some of the other people that we had, I mean, they were almost not leaving on Wednesday until like 1 p.m. or 3 p.m. flight. So they had a whole another half day.
Yeah, I think for me, leaving later doesn't let you catch the connection to San Francisco.
How many minutes did you plan for this?
I've been told 40 minutes plus 10 minutes question, so I'll try to stick to the plan.
First regard soon, you know how it happens.
Yes.
If you go past the time, then they start leaving one by one. And
No, that's sad. I'll try not to do that. Yes.
and having time for QA.
Yeah.
It's a good bunch.
Yeah, it's a good idea.
I think we can go ahead.
NPRE 4590 something. Today we have Lorenzo Vergari, who is a PhD candidate at University of California, Berkeley, in nuclear engineering. He's a member of the SALT research group. As a part of it, he does research on experimental and computational methods in chemistry and engineering of coolant and blanket materials and their interaction with other materials. And today he'll present on chemistry and physics of graphite in fluoride salt reactors. Very timely and relevant topic for us with our graphite reactor. So we all have similar problems, even though there'll be no salt. But other problems still persist. So go ahead.
Thank you. I'm very glad to be here giving this talk. Today I'm going to talk about three things, mainly graphite, fluoride salts, and reactors. So I figured it would make sense to start by introducing each one of them. And let me see if this works. It does. Great. So the first thing that I wanted to talk about is fluoride salt reactors. So fluoride salt reactors are a class of generation 4 reactors. But generally, when we say fluoride salt reactors, we refer to two different types. We have MSRs, so molten salt reactors, which are reactors that employ salts that contain fissile material inside. And we call them fuel salts in this case. So uranium fluoride, for example, thorium fluoride are an example of these fissile salts that are included in these fuel salts. A second class of reactors is FHRs and fluoride salt cooled high temperature reactors. In this case, now the fissile is not in the salt, but the salt is actually acting as a coolant. These are more standard as type of reactors because the fissile material is contained in solid spheres, in solid elements. And so the salt is acting just as a way to remove the heat, move it to another salt that then pass it again to another liquid that goes into the turbine. So in both cases, the salt is there in the primary core, but the role that the salt does is very different. But anyway, for both types of reactors, the presence of the salt is very important. And someone might ask, why? are fluoride salts so crucial to nuclear engineering, so that two different types of reactors are actually planning on using them? Well, there are a few parameters that make these salts really appealing to engineers. And the key points are in terms of their chemistry. So these are salts. So as salts, they have high melting points, but more importantly, they have very high boiling points. What happens is that in nuclear engineering, in order to produce heat at the maximum efficiency with the maximum yield, you want to increase the temperatures of your system. So when you're looking at water, light water reactors, for example, you try to find strategies that can let you increase the temperature of the water without causing boiling. So what you do is generally you pressurize. Now, when you're looking at the salt that does not boil up to 12, 13, 14, 1500 Celsius, then it's enough to increase the temperature. You don't need to pressurize the system. So this brings a huge advantage in the sense that your reactor does not have to have thick walls so that you can pressurize. And at the same time, every safety accident that involves high pressure events is removed by design. A second important parameter that makes these salts very appealing is how effective they are in extracting heat. And the metrics that we use to quantify their effectiveness in extracting heat is generally the product between the density and the specific heat. And for fluoride salts that we use in nuclear applications are generally twice as large as water. So they're twice as effective at extracting heat. And finally, whenever you're putting something in a nuclear reactor, you always have to care about neutrons. Fortunately, these salts are actually very, very good with neutrons in the sense that for thermal neutrons, what we care about is something that does not take the neutrons away, so does not absorb neutrons and potentially slows them down. This is excellent because in this case, we're dealing with salts that do not contain high neutron absorber elements and also very low in Z, in atomic number. So they're actually good at moderating neutrons. And in this presentation, I'll be talking about multiple types of salts. So I wanted to give a couple of names that you will find later. So when you talk about salt coolant reactors, so FHR, the typical salt we deal with is fluoride, which is the eutectic mixture of lithium fluoride and beryllium fluoride. And to make an example of the company that is using this salt is Kairos Power in the Bay Area. When we talk about these type of reactors, we often introduce the term FLINAC. This is another salt. And the reason why this salt is mentioned is not that it's very good for nuclear applications, but it's rather a surrogate, an alternative to fluoride that is often used in the laboratory context because it does not contain beryllium, which is toxic. So many experiments have been run in the last 20 years using this salt as an alternative. When you move to fuel salts instead, so the type of salts that are used in the molten salt reactor experiment or in any MSR, typical examples, as I was mentioning, include also thorium fluoride and uranium fluoride, and the non-fissile salts might include the lithium, the beryllium, and the sodium fluoride. The third element that I want to introduce, which is the one that I care the most about, is actually graphite. Now, graphite is an allotropic form of carbon that is readily available in nature. However, when you go into a nuclear reactor, you don't find the same graphite that you would find in nature. Specifically because the graphite that you find in nature is generally natural graphite, which is single crystal or few crystals. And the main problem with this graphite is that it has two different behaviors depending on the direction where you apply force, where you make changes. So when you try to put this type of graphite in the reactor, it would really behave differently depending on how it's oriented. In a reactor, we do care about having properties that are isotropic. So whatever happens, the graphite change in the same way. And we don't have pieces that are becoming larger, pieces that are becoming thinner, and losing the contact, which is thermal and mechanical. So the graphite that is often used is polycrystalline, and it's very isotropic. And we generally refer to this graphite as nuclear graphite because it has been purified extensively to remove any absorbing materials that would damage the neutron flux in the reactor. And when you look at graphite, you would see something like this image right here that is taken on an SEM scanning electron microscope. So it looks very rough. The reason why it looks rough is that it's not a continuous material, but it actually contains domains of material, of carbon atoms, with domains of pores. These pores are in the order of micrometers, 100 micrometers at most. And they really depend on the type of graphite and the way it's manufactured. We call them micropores. Now, if you zoom in, if you're able to take a TM, for example, and zoom in on one of these grains, you would see that you would have the same distribution between material and porosity. Because even in this case, it's not continuous. You do have crystallites, which are in the order of nanometers to hundreds of nanometers, oriented in every direction, and there is space between them in the order of nanometers again that you would call nanopores. Finally, when you look at the crystallite, then you would see the typical structure that everybody expects from graphite. So these planes of hexagonal, these graphene planes in the shape of hexagonal carbon atoms which extend over a given size, and we define the parameters LA and LC to refer to the width and height of these crystallites. And then when you look at the atoms in the center of these planes, they are the typical carbon atoms with the typical hybridization that you would find in graphite. When you go close to the edge, fortunately, you see carbon atoms that are a bit different because they don't have all their bonds to be satisfied. And so they actually have dangling bonds, and we will see impact dramatically the properties of graphite and its interactions with the rest of the materials. So putting everything together, the reason why we care about salt and graphite when we talk about reactors is that for these classes of reactors that I was introducing, salt and graphite are number 1 and number 2 by volume. So there is a lot of graphite, several tons. There is a lot of salt, several tons. So if we have any interaction between them, then it becomes very interesting from a safety perspective. It's something that we want to know well. And both materials are not that new to the nuclear community. In particular, graphite has been studied for several decades because salt reactors are not the first reactors that make a large use of graphite. Another one that we were mentioning a bit earlier is high temperature gas reactors. So the microreactor and any other technology that was using gas as a coolant and graphite as a moderator uses large amounts of graphite. And so these reactors operated in the past and are planning to operate again. So there has been already a lot of legwork in terms of graphite properties. For example, the way graphite behaves under irrigation or the way graphite behaves under oxidation have been well characterized by research groups. However, when you want to license a salt reactor, you need something more. You need to know what's happening between the salt and the graphite. And this was the big idea, the context behind my research, my PhD at Berkeley. We wanted to understand what are the main mechanisms of interaction between the salt and the graphite, and how this interaction is impacting the very performance of the graphite in the reactor. So today, I would like to go over a couple of the interactions that we would have between salt and graphite, describe them, and then explain them in terms of some topical cases, some examples of applications where these interactions actually changing the performance of the graphite. So we're going to talk about chemical and physical interactions, and the application cases I would like to talk to are tribology, which is also relevant for the microreactor, and sequestration of tritium. I will see why this is relevant for fusion as well. So the first topic are the interactions, and the first interaction that I want to talk about, if this works again, is chemistry. So why chemistry? Well, we're looking at carbon. Graphite is made of carbon. We're looking at salts that contain fluorine. And we know that actually a lot of different types of chemistry and sciences have cared about these two materials because they're known to react a lot with each other. There have been a lot of studies in many branches of sciences showing that the properties of carbon materials when they were exposed to fluorine-containing compounds have changed significantly. I'm showing here just a few examples on these slides. They don't pertain to the nuclear engineering sector, but just give you an idea of how important the reaction might be. So on the left part, you're seeing carbon fibers, which have been exposed to fluorine gas for some time. The more the higher the temperature or the longer the exposure, the more their color changes. It's not just color, it's also physical and chemical properties. So for example, the electrochemical properties, the charge capacity, the conductivity of graphite in carbon materials change a lot depending on how much fluorine you're able to introduce in your graphite. The amount of gas that the graphite itself can be trapping, can be keeping far away from the rest of the system in its pores and attached to its surface change a lot depending on the content of fluorine. And finally, the effectiveness of graphite as a lubricant. We all might know that graphite is very good at shearing. Well, this effectiveness changes a lot depending on how much fluorine you might be able to introduce in your carbon materials. So all these examples suggest that it might be really interesting to actually look at these properties and see what is happening. So is there some reaction that might take place? Because again, several tons of one, several tons of the other ones, if the properties changes, this is massive. And if you look at thermodynamics, the answer is very reassuring in the sense that we should not expect any reaction that takes place between the graphite and the salt constituents that we would find in the reactor. So what I'm showing here on the left side is an elegant diagram. Chemists might be familiar with this. So this is the diagram that is showing the energy of formation of compounds, against free energy, as a function of temperature. The way you read this diagram is that considering that every line corresponds to the formation of one specific compound, if the line is lower in the diagram, it means that that compound is favorably formed compared to compounds that have lines that are in the top part of the diagram. So you could think of a reaction that is leading to the formation of fluoride by reducing the other elements. And so if you look at two lines and you see that the fluoride that you want to form or you're afraid of forming is below the one that you already have in your system, then that reaction is actually taking place. But if you look at this diagram, you see that every line that corresponds to the constituents of the salts, so for example, the beryllium line, the lithium line, or even the lines that might be associated to some corrosion products that you might find in the salts, so chromium, iron, all these lines are lower than the lines associated with any reaction you could think of about carbon. So this suggests that reduction of fluoride, either pure fluoride or fluoride with corrosion products, by carbon materials should not be expected, in theory. In practice, though, there are studies that show otherwise. So this is just an example that I'm showing for about 10 years ago, in which one group exposed one specific grade of nuclear graphite to FLiNac, the surrogate salt that I was mentioning earlier, for a few hours, and saw that some bonding between carbon and fluorine was happening. In that case, they observed that the hydrogen that originally was in the graphite was going away and was being replaced by fluorine. So some reaction was actually taking place. So this motivated my group, even before I joined as a PhD student, to start running some experiments to see whether these type of reactions could take place also with FLiNac, the salt that is actually used for these type of reactors directly, so not with the surrogate. So there was an experimental apparatus that was built in order to expose graphite coupons to the salt for several hours at high temperatures, 700 degrees Celsius, in our environment. And after the exposure studies were done, I was tasked with characterizing these samples and understanding if something was happening. And the first thing that I did, of course, was looking at the samples themselves using a microscope. And I'm showing here on the top part microscopy with scanning electron microscope and electron dispersive spectroscopy to show what's there on the surface. And you can see the rough surface that I was mentioning earlier for graphite. If you zoom in, you see in the pores, there are some spheres. And if you look at the sign, the symbols from EDS, you see that these two correlate pretty well with fluorine. So there is something with fluorine in the pores. Okay, what is it? Well, we suspect this is lithium fluoride or beryllium fluoride, so the constituents of the salts. The reason why we think so is that EDS, the technique we're using here, does not probe for lithium or beryllium. So if you just see fluorine, then it's very likely that it's either lithium fluoride or beryllium fluoride. But this doesn't mean that there is a chemical reaction taking place. You're just seeing the constituents of the salts in the pores. So there is some intrusion, yes, but does it mean chemical reaction? Not necessarily. However, when you use other techniques that probe the chemical environment, and X-ray photoelectron spectroscopy is one of them, you actually see that not only there is a peak associated with fluorine that is saying that there is a fluorine content, a few %, but also when you zoom in on that peak, you see that the peak is associated to carbon fluorine. So there is actually a reaction taking place. So why does thermodynamics tell us that there is no reaction? And why do we see the reaction instead? Well, the hypothesis that we put through, and also the other group thinks the same way, is that actually, when you look at thermodynamics, you generally refer to those carbon atoms that are in the center of the hexagons, that are in the center of the planes, that are fully forming hexagons, so they don't have any spare electrons that they can use for other bonds. However, when you have a finite sized piece of graphite, you have a lot of those tiny carbon atoms at the edge that have plenty of electrons that are willing to share and bonds that are willing to form. And so what really is reacting is not the normal carbon atoms, but it's rather the edge carbon atoms. And so graphite does have some reactive sites that we show are reactive to fluorine. So these reactive sites are just at the surface of the crystallites. There are not that many of them. And fortunately, the salt does not have that much power at reacting with the bulk of the graphite, but we do see some superficial reactions. So this suggests that actually fluorination of graphite is taking place. It's a chemical phenomenon. And if we are able to keep the salt away from the bulk of the graphite, then this is pretty reasonably manageable because it means that we're just reacting a little bit of atoms on the surface of the carbon. But for some reason, if salt does enter the graphite, then we might have a problem because this reaction would not limit itself to the surface, but would proceed in the bulk of the material. So the next step is, how can we understand if salt enters the graphite or not? And this made us focus a bit more on some physical interaction mechanisms, and specifically salt infiltration in graphite. And this topic is not new. If you were in the 60s, and many of us were not, you would find out that in the molten salt reactor experiment in Oak Ridge, they were really afraid about infiltration. They chose the graphite grade to be specifically impenetrable to salt. That was priority number one. they chose a graphite grade that was really bad for a lot of perspectives, was really anisotropic, but at least it was not penetrable by salts. Their tolerance to infiltration of salts was very limited. Already 1.5% was the design limit, and 4% was completely unacceptable. Why was that important for them to avoid the infiltration? They were not focusing on the chemistry. They did not have the same chemistry concerns that I was mentioning a little bit earlier. They had other concerns. The first one is that MSRE, molten salt reactor experiment, is an MSR. So they don't have a salt coolant, they have a fuel salt. So what happens when you have a fuel salt? You have uranium, you have fission products in your salt. So if the salt enters the graphite and it stays there, it brings with it uranium and the fission products. And see, if it brings the uranium, it brings in the fissions. So locally, you would have fissions which lead to a temperature increase so large that the graphite resistance to irradiation in that specific locations would really decrease significantly. And so your graphite components would basically break. Similarly, even if they don't break, because you're able in one way to reduce the amount of fissile material inside, you bring in fissile fission products. And some of these fission products are known neutron poisons. So when you have a neutron poison in your moderator, that's surely not a good sign. So they really have very tough limits in terms of infiltration. And these apply to MSR design also today. But when we consider all the plurality of molten salt reactor design, so including also those that use coolant salts instead of fuel salts, you can think of other reasons why infiltration might be not that great. So even if you don't have the fissile materials, you might have the introduction of an external element in your graphite, and a reactor does change temperature. It's not really steady state. So you have temperature excursions up and down. So what happens is that if you have something that can actually solidify inside, you would have something that solidifies, changes volume, creates stresses, then it melts again, and then solidifies. So you keep doing thermal stresses, and that could significantly damage your graphite, especially if it's a structural material. Moreover, there is a chemistry concern that I was mentioning earlier. If you let the salt in the graphite, the surface area of contact between the salt and the graphite increases significantly. So the reactions that could take place at the surface before now can take place also inside. And potentially these reactions can open the door to a lot of other phenomena that might be very damaging to your graphite. Typical example is oxidation. If you see that these reactions between fluorine-containing salts and graphite lead to the increase of reactive sites, then this could lead to a significant damaging of the oxidation resistance. Another example is tritium that we'll see very later towards the end of the presentation. But the key point is that in fluoride salt reactors, there is a lot of tritium, and we'll see why. And if you change the graphite, then this graphite might actually be pretty good at catching this tritium, which means that if you at some point release the tritium because of an accident, you might have a very large source there. So the safety transients in general would change significantly as you might have an infiltration in the salt, of the salt in the graphite, which motivates to understand if the infiltration is taking place or not. So as every PhD researcher, I started this by doing literature review. And I looked at the studies that were doing salt infiltration of salt in graphite. They were quantifying it, and there were many of them. So the first thing you can see is that there is generally a trend that suggests as you increase the pressure of the salt, more salt enters the graphite, which is reasonable. Second thing is to notice is that all these lines are in different locations on the y-axis. So there is a very strong variability in terms of the graphite grade. And most of them are actually above the 4% limit at the pressures of interest for these reactors. So this is not that good. The third more concerning thing is that when you look at lines that have the same color, which refer to the same graphite grade, you see that they're not really coincidental. So there is something more that is not explained by the graphite type, but some other parameters are actually impacting significantly how the salt infiltrates graphite. So in order to understand why that was the case, we started looking a little bit at the equations that regulate salt infiltration in graphite. And fortunately, this is not that complicated. There is one equation that is very simple. It's the Washburn equation, which studies capillary flow and basically tells you what is the pressure required to infiltrate with a liquid a pore of diameter d. Now, when you look at graphite, it doesn't really have one pore. It has many pores of different sizes. So you would have a distribution of porosity. Since you know this distribution of porosity, you might be, in principle, able to calculate at a given pressure level how much of this porosity is infiltrated. So you would be able to see whether this total porosity is above 4%, below 4%, it's above a given other limit, which might change with respect to the MSRE or not. But the condition is to do this type of calculation, you need to know these other two parameters that are in this equation, the surface tension and the contact angle. And these are wetting parameters that depend on how well the salt is able to wet on the graphite. And these wetting parameters depend on many things. They depend on the salt, on its chemistry, they depend on the graphite, on its surface finish, and they depend on the environment. So our expectation is that when we see studies that with the same graphite grade, same conditions, same pressure, obtain very different infiltration pressures, infiltration amounts, there are really different conditions in terms of either of the graphite and the way it was done, or the salt chemistry, or the environment. And I'm showing you on the right side one typical example of how this contact angle may change. So this is a very old image. I'm sorry, I didn't take it. So you could see that the first droplet that you see on top is very spherical. The second one is very flat. It's the same graphite, it's the same salt. In one case, there was moisture in the environment. In the other case, there was not. So this suggests that really knowing the conditions at which the experiment you're doing will impact significantly your result. So we started having an interest in actually measuring these parameters, measuring the surface tension and measuring the contact angle, because we knew already the distribution of porosity. So we said, if we know the contact angle, we know the surface tension, since we know the distribution of porosity, we're then able to calculate the pressure that is required to infiltrate, and then compare it to the reactor pressure and see whether we are having infiltration or not. So what we did, and this is a collaboration with an undergraduate in chemical engineering in my school in Berkeley, was develop a setup to measure contact angle using the style drop method. We have a glove box, we have a tiny furnace with a window, and we're able to make graphite samples and droplets of salts with different salt chemistries and different type of graphites. And we're using a high resolution camera outside of the glove box to take images. And then we made a script in Python to look at the images and extract from there the shape of the droplet and its size, which let us measure the contact angle and the surface tension. So today, I just wanted to show some images very quickly about this, because I would like to move to other topics as well. But if you do find this topic interesting and you're joining the ANS student conference this year, Zach, the student that worked in this project, will be giving a full presentation on this. So I welcome you to attend this presentation and talk with him as well. So just to give you a few ideas of how the wetting is changing, I wanted to show these few images that show the shape of droplets of salts when you add a different amount of additives or you change the salt. And so what you can see actually is that Flav and Flynak are there. This is a very nice image. It was taken back in Wisconsin before I joined the group. The other one's unfortunately a bit lower qualities, and I'm responsible to it. The camera was not as good as the other one, but the photographer was helping for them, so we had extra support. But if you look at the images, you actually see that the shape of the droplet changes significantly. And between Flav and Flynak, there is a difference. But then when you look at the same Flynak and you add very small amounts of either an oxide or a metal, then the shape becomes even less spherical or more spherical. If it becomes less spherical, more flat, it means that it wets more. It means that the salt really wants to enter the graphite more easily. So the infiltration resistance will actually worsen a lot by introducing even a small amount of oxide in your salt. And at the same time, by adding some reducing metal like aluminum, the shape becomes way more spherical, which means that the salt infiltrates less. So small impurities will change significantly the chemistry of the salt and significantly the infiltration properties of the graphite, the resistance of the graphite. Another example of things that will change a lot the properties, the infiltration resistance, is the surface finish. So we run some experiments polishing the surface of the graphite. We run some other experiments removing the moisture from the graphite by baking at high temperature. And we saw that the contact angle and the surface tension were actually changing. So something interesting is that when you remove the moisture from inside, the contact angle becomes larger, so the salt becomes less wetting, which is very similar to what they saw in the 50s in the molten salt reactor experiment. And at the same time, when you move from a smoother surface to a rougher surface, the contact angles actually becomes smaller. So in this case, becomes more wetting, more infiltration. So it is interesting because actually there are phenomena in the reactor that will change the content of oxygen and moisture in the graphite, oxidation, for example. And there are phenomena that will change the rough or smooth surface of the graphite, irradiation. So this actually tells us that even if you have the same salt with the same salt chemistry, just time will change how much the salt will infiltrate the graphite. And what I'm showing here on the right side is just an example of how we can use this data on surface tension and contact angle to predict at a given pressure level how much salt will be infiltrating in the graphite. And this is just an example, but the numbers are very high. So with this specific graphite grade, we saw that even in the best conditions that are shown here, at least 11% of the volume of the graphite would be infiltrated at pressures that are compatible with HRs and MSRs. So this suggests that actually infiltration will be a significant issue and will need to be studied even more in the next few years, also including the effect of oxidation and infiltration. Now that I've given a few minutes on this mechanism of interaction, I want to give another example, a couple of examples to explain how they are relevant for phenomena that we see in the reactor. And so one of the examples that I chose to present today is about tribology, because it ties very well to what's happening here in Illinois, so the microreactor. So tribology is the science of friction, wear, and lubrication. And you want to know friction, wear, and lubrication whenever you have rolling items, especially when these rolling items are pebbles that contains graphite, that might contain chrysal particles inside, for example. They are rolling against each other, like in HDGR designs or FHR designs, roll against the wall. And as they roll, they will change the velocity because of the friction coefficient. So if they change the velocity because of the friction coefficient, what happens is that they will stay longer or for a short period of time in a reactor. Now, since the fission is actually happening in this sphere, if you keep the sphere longer or for a short period of time in your reactor, also the amount of fissions that it will generate will change. So also the content of fissile as these pebbles are coming out of the reactor will change. So the burnout in general will change. Now, if you move to wear, if you think about the damages that these pebbles will undergo as they roll and hit against each other, you'll think that there will be some dust that is generated. Graphite is very dusty. But this is not normal dust. This is dust of a graphite sphere that was in a reactor core. So if there were fission products, if there were isotopes that are radioactive on that, then you should consider this a radioactive dust that is spreading all over the place in the reactor core. It might go on the heat exchanger, impacting your heat transfer properties, or it might go somewhere else and be an inventory of radioactive material that you then have to decommission. And finally, lubrication is crucial because there are a few mechanisms of lubrication that rely on chemistry. And at the same time, when there is lubrication, there might also be corrosion. So the lubrication and the corrosion and the interaction between salt and graphite might actually reinforce each other. And so we would see some phenomena that we would not see when we have no motion. And at the same time, these could lead to different effects in terms of wear and friction. So the phenomena of chemistry and tribology are actually intrinsically related to each other. So we wanted to quantify this. And this was a topic that was also very relevant to Kairos Power, the company in the Bay Area that is making FHRs. And so to try to quantify the coefficient of frictions, we looked at the studies, and we could find a lot of them. Once again, graphite friction is very relevant. It was studied in the aviation industries more than 100 years ago. So it was important that there were a lot of studies that we could find. And what we could see is that the environment really matters a lot. So when you study graphite friction against graphite in air, you get coefficients of friction that are as high as 1. Then if you use inert atmospheres, then it goes down around 0.5, 0.6. If you go into water, it gets down to 0.2, 0.3. So for the salt, if you had to estimate a coefficient of friction based on this data, you would have an error bar that is gigantic. Because unfortunately, there are not that many studies of graphite friction in salt. Specifically, there is just one, which is not even peer-reviewed. So this was a strong motivation to start an experimental campaign to actually measure coefficients of friction and wear of graphite in salt and understand what the mechanisms were. So in Alameda, California, the headquarters of Kairos Power, there is a glove box that was used to define this experimental high temperature apparatus for tribology measurements. It's a system where there is a sphere that is a given graphite grade, ET10, which is the material used for the reflector, that it's kept steady, constant, with a load applied on top. And then there is a disk of another graphitic material that rotates against each other. And as it rotates, there is a load cell that is measuring the resistance to rotation. And then looking at the imprint that we form on the two components, we're able to calculate the volume of mass, the mass in general that goes away, and so the wear rates. And so we ran these tests and we looked at the results of the tests, so the friction coefficients and the wear rate. And we also characterized the samples to understand what type of mechanisms were actually taking place. So the first thing that we looked at were the results of the test, so coefficient of frictions and wear rates. And we decided to run 3 different tests or 3 different classes of tests. Our goal was to understand what was happening in the salt. But we knew that when you were running some tests in the salt, you were intrinsically running tests at high temperature. And our goal was to understand what was the effect of the individual salt. So we wanted to decouple this from the effect of temperature. So we decided to run tests in argon at room temperature and high temperature. And then at the same high temperature, 600 degrees Celsius, we also run tests in salt. We run tests in Flinac and Flibe, so the 2 key salts. In this presentation, I'm only showing the results in FlyNAC, but hopefully the results in Flight will also be published recently, in the close future. So in terms of results, the plot on the left is showing the coefficient of friction, so the resistance to sliding, basically. And you can see 3 lines with 3 different behaviors. So the red line, which is the room temperature line, is higher up. So this indicates that there is a highest coefficient of friction at room temperature in argon. Then as you increase the temperature, the line goes down. So you have a lower coefficient of friction, still in argon, but higher temperature. And finally, when you add the salt in the system, the coefficient of friction becomes even lower. So this suggests that there is some sort of lubrication that is taking place because of the temperature, and some sort of lubrication that is taking place because of the presence of the salt. And the same behavior is suggested by the wear rate. So we see a very high wear rate with a lot of variations in the a large standard deviation in room temperature argon, lower wear rate in high temperature argon, even lower in FlyNAC. So why is this the case? If you're interested in engineering, this is probably enough as of an answer because you know the coefficient of frictions and where your reactors, so you can make models to explain what's happening and quantify the amount of graphite dust that you generate. But if you're interested more in the chemistry, you might want to do some additional characterization to see what's happening. And first characterization that we did was looking at the surfaces of these components that we were rubbing against each other. So in this type of tests, what you generate is an imprint that is circular, and the size tells you how much wear you're generating. So we use some microscopy techniques to understand what type of morphology we're generating. And the first type of microscopy we used was digital microscopy. And the digital microscopy we used are actually coaxial light, so light coming from the top. And for all these tests, we saw a different combination, different ratio, a pattern between darker regions and lighter regions. So when you're doing coaxial illumination, which means light from the top, if a region looks lighter, it means that it's more smooth. When a region looks more dark, then at the same time, it means that it's rougher. So this suggested there was a combination of smoother and darker regions. And coincidentally, or not coincidentally, this combination was more richer of lighter regions, so smoother regions, when the coefficient of friction was lower. So high temperature in both argon and FlyNAC, and was richer of rougher regions, darker regions, at room temperatures when the coefficient of friction was high. So this started to suggest that when there is a mechanism that leads to a smoothing, this might lead to some lubrication. This was confirmed by SCM. So SCM shows clearly that there is a smoother surface at high temperature with respect to room temperature, and also suggests that there were some grooves that were forming, and these grooves had the opposite behavior. So we had more grooves actually when the coefficient of friction was lower. So we started thinking that there were 2 mechanisms at play. And then we added a third technique. This is polarized light microscopy, which is actually a technique very helpful when it comes to graphite. And if you're familiar with EDSD, this is very similar, but for graphite instead of metals. So what it tells you is how aligned, basically, how isotropic or anisotropic the distribution of crystallites is. And the way you analyze this is that when you see a more uniform color, it means that the crystallites are all in the same orientation. When you see a more disuniform color instead, this suggests there are multiple orientations. And so we saw that at room temperature, there are multiple orientations. And as you increase the temperature and added the salt, your orientation, the color became only 1. So everything started suggesting that we were forming some sort of a film. And this film was actually helping the lubrication of the graphite. The final piece of the puzzle was provided when we introduced the last method of characterization, which is Raman spectroscopy, which is another technique that is super helpful for graphite because it does give you direct information about the size of your crystallites. So what we saw is that when we selectively probed points on the film and outside of the film, the Raman spectra was very different. And when you run your calculations to see how this correlates with the size of the crystallites, you see that on the film, these corresponded to very much smaller crystallites, about half in size in one direction, same size and thickness, compared to crystallites in the rougher regions in the wear spot and also outside of the wear spot. So putting everything together, we formulated an hypothesis that suggests that actually what we're seeing when we are wearing graphite is that we are fracturing crystallites perpendicular to their basal planes. And these crystallites are really trying to align each other so that they're always facing with one plane, the other material. And the plane they're trying to expose to the other material is the one that is less chemically reactive. this alignment mechanism is more favored at high temperature than at room temperature, and becomes even more favored when you introduce salt, because the salt is able to passivate somehow these very active sites of graphite, and so favors their alignment even more. Finally, the last topic that I want to talk about is something that is more relevant to the fusion people in this room, and it's the topic of tritium. And I'm more of a fission person in terms of my PhD studies, but tritium was still a key topic for me. And the reason fission was such an important topic for me is that for molten salt reactors, tritium production rates are incredibly high. Since these reactors contain lithium and beryllium, and the neutron activation reactions that involve lithium and beryllium and produce tritium have such a high cross-section in these systems, you might have production rates that are a couple of orders of magnitude larger than light water reactors. So you produce a lot of tritium in these reactors. And since now we have some fusion technologies that are starting to think about using blankets, breeding blankets that include lithium and beryllium, the same topic about large tritium productions in salt is becoming more and more relevant also for the fusion community. But if you look at the fusion community, that tritium is a fuel. So you want to collect it and use it. If you look at it from the perspective of a fission community, that tritium is a problem because it's a contaminant. And what happens is that tritium, unfortunately, does not have a high solubility in the salt that we're looking at in fly, which means that if you're producing tritium, it starts going up in the gas phase and it starts building up its partial pressure. Now, tritium is an isotope of hydrogen, which means that it can go through metals very fast. So if you think about a system where you are increasing the amount of tritium in your cover gas, it's tritium gas, so think about it as hydrogen gas, you have metal structures, all the tritium is very happy to fly away from your core through any metal structure. So you end up having a constant source of tritium into an environment, which is definitely not a good strategy, which suggests that you need to have some way of reducing the inventory. Fortunately, it seems that graphite is actually a good way of reducing that inventory. Back again in the molten salt reactor experiment, which is the first large-scale example of how these systems employing molten salts would work in the real world, they had some issues in quantifying how much tritium we're producing because the numbers were not rounding up. And they found out that about 20% of the tritium that was being produced was actually in the graphite. So they started expecting that there was some chemical mechanism leading to tritium being trapped in the graphite. So this motivated engineers more recently that are thinking about fluoride salt reactors to actually use the graphite spheres that normally go in and out of the reactor because you want to cycle them through the salt and then take them away, analyze them, and perhaps reintroduce them, to use them as actually sinks for tritium so that they can trap tritium. They could be a vector for this tritium out the core. You can release the tritium in a controlled way, and then you can reintroduce them. So the idea of using graphite for tritium managing is not new, but it's still in its very early stage because the first question that you need to ask in this case is graphite enough? Is it capable enough of trapping tritium that is in the core? Do we have the right amount of graphite? Do we have the right amount of tritium to allow for this reaction to take place? And so we wanted to understand the question, to study the engineering case of graphite as a way of trapping tritium. And so we started looking at the studies, and even in this case, we had many studies for tritium and hydrogen isotopes trapping in graphite. And for the next 5 minutes of the presentation, which are also the last one, I'll be talking about hydrogen or tritium interchangeably because their chemistry is pretty much the same. So we looked at every study that involved hydrogen and graphite and started to understand how much hydrogen could go in graphite, because that would inform whether our pebbles would be a large number enough to contain all the tritium. And what we saw is that there were a lot of studies, but we had two main problems with these studies. I'm plotting them here as a function of pressure and temperature. What you can see is that, first of all the studies are high pressure and pretty high temperature. The reason that's the case is that these studies mostly run by the fusion community that was interested in hydrogen graphite interaction properties for diverter purposes, because graphite was expected to be a plasma facing component. So high temperatures were expected. And secondly, when you're running an experiment with a gas, you'd like to run an experiment at high pressure because the sensitivity of your instruments will be finite. So you'll get better resolution, better results at high pressure. So if you look at the region in blue, which is the one of interest for these type of molten salt reactors, you don't really see that many studies. So you need to find a way to move from the studies that are in all this region at high pressure, high temperature to this tiny region of interest for you. Second problem is all these studies were actually run in gas conditions. So all the hydrogen was introduced into graphite as a gas. So we don't know actually if this is relevant for fluoride salt reactors as well, if the behavior that we would see is the same when we apply the salt or not. And so our group started to investigate these two questions separately. We were able to find the conclusion on one of them, and we're still finishing up on the second one. Hopefully the next few months will be decisive on that. So for the first question, so trying to get to understanding whether at our conditions we can extrapolate the results, we were able to generate models to actually look into that, and I'll talk about this in a minute. For the second question, so understanding whether the presence of the salt would impact at all the mechanisms that are happening between the salt, between the graphite and the hydrogen and tritium, we're using electrochemistry as an experimental technique. So for extrapolating, we need to know the mechanisms. That was the first step. And we've actually found out that the chemistry of hydrogen and graphite is very complex in the sense that when you try to introduce hydrogen and graphite, there are multiple locations within the graphite crystallite where it can go. And mainly there are two locations. The first one are the crystallite edges, which are the same reactive sites I was mentioning earlier on. The second one is inside the graphite crystallites. But however, whatever complexity these mechanisms might be, they can actually be modeled. There are some energies that are associated with hydrogen or tritium trapping in these sites. There is a given abundance of this site. So you know the temperature dependence, you know the pressure dependence, you can write your equations to predict for a given condition in pressure and temperature how much hydrogen would be there. And we also have a lot of data. So the first thing that came to mind was, well, let's make this model and let's feed it to the data. Let's try to extract the parameters that we need to know. The most important ones were the abundance of these trapping sites, so that we can understand whether the conditions that are of interest for us, we can actually use this graphite or not. Unfortunately, the results were not that pleasant in the sense that we tried fitting this model and we saw that the errors were very large. For some graphite grades, it was around 20, some others were 25, 30, 35. So definitely we're not able to model this properly. The feeding was not working very well. So we started asking ourselves, why is this not working? And the idea that came to mind is actually that we were forgetting about a variable, which was time. And the plot here is showing the importance of time. So this plot is showing the amount of hydrogen that would go in graphite at the same pressure and temperature when you increase the exposure time by a factor of, by different factors. And you can see that the amount can change significantly until at some point you don't run the experiment long enough so that you reach the solubility limit. So we understood that actually those data we're looking at that many groups have thought were solubility limits. So the maximum amount of hydrogen and tritium that could go in the graphite were just what they measured. And sometimes they did not have enough patience to run the experiment for long enough. So the data were unfortunately not complete. We were not able to give an answer based on that. And we had to generate a model that now started to include time as one of the variables in addition to temperature and pressure. And so this is a collaboration that we did with computer science. We're able to generate a model for hydrogen trapping in graphite, exploring a bit more of the hydrogen graphite interaction, starting from the examples of metals that has been studied also by members of this department in the past. So we generated this model. We're actually able to fit it very well to data, and errors went down from the 25–20% that we saw before to about 3%. And one of the byproducts was that we are actually able to extract the abundance of these trapping sites in which hydrogen can go. And so we're finishing up this project now, trying to put together this information with the production rates that we have calculated to see whether we can actually use this graphite to extract a significant amount of the tritium every time these graphite pebbles are coming out of the core. And the last couple of slides that I have here are about what's still being done in our groups, which is answering the second question. So we've seen that we've been able to extrapolate, but how does this extrapolation change as we introduce the salt? And something we're developing right now are some electrochemical techniques to actually explore the effect of the salt in hydrogen uptake and desorption. And the technique we're trying to develop right now is very similar to what is done in gas studies, and it's called thermal desorption spectroscopy. This is a very mighty technique that lets you take a sample that has some hydrogen inside, heat it up at constant rates, and as the temperature increases, you start releasing some hydrogen. And the way this hydrogen is released, so the rapidity, the velocity at which this hydrogen is released, the amounts as a function of temperature will actually tell you where hydrogen sits, so in what locations, what energy is associated with these sites, and what is the amount of these sites. And so we're currently working on this, continuing an experiment that was started a few years ago and then left. And we're trying to generate this data in 5 salts so that we can actually understand whether all the data that we were generating in gas can actually be directly translating into 5 or not. So to conclude, today I wanted to give a very quick overview of some of the interaction mechanisms that we've been looking at Berkeley to try to understand what's going to happen when graphite is being exposed to salt for a long period of time, which is relevant for different types of reactors that actually employ molten salts. The key points that I wanted to make is that we see that all these mechanisms are very interesting in the sense that they're going to change the properties of the graphite, and they're not really independent from each other. So one mechanism, chemistry, for example, might lead to better or worse properties of the graphite in terms of tritium trapping. And at the same time, some physical mechanism, like infiltration, can lead to impacts on how large the chemistry of the reaction is, how impactful the chemical reactions are. So overall, this seems to suggest that there is a lot more study that needs to be done in order to have graphite being licensed as a component for molten salt reactors. And things become even more challenging when irradiation enters the picture. And so our group was not able to run irradiation because we don't have a reactor in Berkeley, but I would expect the introduction of irradiation in the picture, in addition to exposure to the salt and high temperature, to be very significant in determining whether graphite can withstand the salt exposure for a long period of time while still remaining functional. So to conclude, I would like to leave it here, showing the picture of the people that are being working in this project. This is my group at Berkeley. As I was mentioning, one of the students, Zach Kolkowski, is going to present some of the results for infiltration at the ANS Student Conference in Knoxville. So if you're going there, please reach out to him. He'll be very happy to present you with some of the results. And otherwise, I'm very happy to take any questions you might have on this presentation. Thanks a lot. Yes.
Thank you so much. This is a fascinating talk. So all of this, like, deeper understanding and characterization of the graphite crystal, I was looking at it from a bigger picture. Like, how do you think this will impact how we can, like, manufacture or operate, like, for the graphite and then operate the reactors?
Yeah, that's a good question, because it ties in one of the biggest problems that are often not talked about in nuclear engineering, which is cost. So all the studies we're doing right now are trying to understand how the properties are changing with time. And the key point is understanding how long these components are able to stay in the core while still being functional. So this is going to impact how long we can keep the graphite there. And if the graphite has at some point to be removed, this is going to impact the cost of the reactors, because either you leave the reactor as is and you just close it, or you remove the graphite and you put another graphite piece. So ultimately, this is going to have an impact on the cost. And unfortunately, this is going to be an impact also on how effective this reactor will be, because if the cost will not be sufficiently low to allow for a levelized cost of electricity that will be matching the competition, then it's going to have an impact on whether these reactors will be deployed or not.
Can you talk in general a little bit about the effect of impurities? Maybe that's after your comments about salt chemistry. Just talk about impurities in terms of lab scale to industrial scale or something like that.
Yeah, so this is another topic that is very interesting, because there are a lot of graphite vendors right now in the world that are trying to make graphite grades that have very low amount of impurities. The need for graphite with low impurity content is well understood and was understood already for gas graphite reactors. Because, for example, boron is one of the impurities that you might more easily find in graphite, and boron is a strong neutron absorber, so you want to avoid that. So from a neutronic standpoint, it is known that having impurities in the graphite is a problem. What is a little bit more complex is controlling the impurities in the salt. Because while in the graphite, you know already what impurities are there, and it's more difficult to introduce some additional impurities unless these are fission products that are staying there. For the salt, the situation is a bit more fluid, in the sense that you might generate corrosion products, you might have the ingress of oxygen or moisture, and so this is going to lead to some impurities present in the salt. And we've seen that the presence of impurities is going to affect a lot the chemistry of the salt. Typical example was the droplets that I was showing earlier. Even 1%, which is still a large amount, but it's not the microscopic of oxide, is actually making the salt wetting. And if the salt becomes wetting, it means that it enters the graphite no matter what the pressure is. So overall, the control of the impurity content in the salt is going to be crucial. And fortunately, groups are developing methods for control of redox potential that will be able to control how many impurities are there, to know what impurities are there and be able to actually remove them.
For the part of thank you first for the great presentation, but for the part of the filtration of the graphite by the salt, would it be a good idea to have like a coating material that acts better than graphite?
Yeah, that's a great idea. And some groups, especially in China, are working on that. Pyrolytic carbon has been considered as an option for coating material because that does not have porosity, so it would be able to keep the salt away. Now, the problem is that if this is a static system, say a molten salt reactor, so you don't have pebbles, you just have the reflector that is made of graphite, the moderator, then you don't have probably anything rubbing against it, so the coating would stay there unless it's eroded away from the salt. But now, if you have a system where you have moving components like pebbles, and these pebbles are hitting against each other, hitting against the metal structures, you'll have some wear, as we've seen. And so if you're coating, that coating might go away. And so you might still have infiltration, even if you started with some coating.
Great, thank you for the nice work, very fascinating work. I have a question about research. Fusion person, that's very interesting. Do you have a set of our treatments to use? It's going to become a very valuable gas. So there are currently researchers that are trying to produce these on a large scale.
Yeah. So I have a number here, 3,900 gigawatt thermal day.
Yeah, I don't quite understand.
So we recently published a paper that tries to answer this very question. So how much tritium is produced in both fission reactors, FHRs, and in fusion blankets like ARC. I don't have the paper right now with me, but I can show it to you later. And yeah, the point of that paper was actually answering this question because it's very hard to understand how much are we really talking about. And so we started looking at that paper as a way to give this number to people. And then it became another story. Maybe this is a story for another time, but it became very interesting to find out that actually production of tritium, in addition to other activation reactions, was going also to have an effect of the total amount of electrons in the salt. And if you change the total amount of electrons in the salt, you're changing the redox conditions. So in that paper, we actually found from a modeling standpoint that activation reactions and tritium production have in general an oxidative effect, a corrosive effect. And so you'll have additional corrosion that is due to activation reactions. But to get back to your question, yeah, at the end of the presentation, I'll give you the number. I'll show you the paper.
There will be a very interesting number now.
Yes.
People are looking at different technologies and
Yes.
produce it.
Yeah.
Maybe last question.
Sure,
Yeah.
just for metal surfaces that have been irradiated, particularly with high purity gammas, there's this activation of the surface and it becomes super hydrophilic with water. Does that happen with graphite?
You know, I don't think there has been an example of this type of mechanism taking place. Unfortunately, there is not a lot of irradiation studies that were done for graphite while that graphite was being exposed to the salt. I remember only one study that was done in Wisconsin a few years ago, but they did not characterize the graphite with those techniques that would tell you how well it was keeping the salts away, basically. So they did not use XPS, for example, to study the chemical reactions taking place. So this is definitely something that will be explored a bit further down the road. What I can tell you though is that irradiation, for example, is changing a lot the graphite properties in terms of hydrogen. Even a very small dose, a very small dPa, less than 1, is going to increase the amount of hydrogen that can be trapped in graphite by a factor of 100. So if you're thinking seriously of using graphite as a way to remove tritium from the core, for example, knowing that that graphite will be irradiated as it's in the reactor, will increase by a huge margin the chances of keeping all the tritium away.
Okay, let's thank. Turin.